Okay, this is our first day focusing on FRQs in particular. And you've been doing FRQs in bits and pieces over the course of the year. Unit 6-7 combo is the one I would say that has been the unit that has been the most FRQ focused. And we talked about that in class several times. So with Unit 6 we were looking at solids of revolution, and like area between curves, cross sections, that kind of thing. That's one of our common FRQs. And then in Unit 7, we looked at two different common types of FRQs. We looked at particle motion, and we looked at slope fields and differential equations. Now, there are three other common FRQs. Each Monday of our review here, we are going to focus on a different one of those common ones. So today we're going to be focusing in on the tabular data and Riemann sums. There are going to be 4 done in this video. 2, or I should say 1 or 2, I would recommend kind of walking through with me. It still wouldn't be a bad idea to pause the video and kind of take a look at them on your own, but again, my thought process, the first 2 that we do here would be for us to do together. And then my recommendation would be to pause the video with the last however many you choose to do it on. I'd say at least 2, but if you want to do it on 3 or 4 of them, that's fine too. But to pause the video, try those last ones on your own. That way you're figuring out what is it in this kind of tabular data zone that you are really clicking with, that makes sense, you know you've got that in the bag, and then what is it in that tabular data zone that maybe is giving you a little bit of trouble. Because these tabular data FRQs are going to keep showing up through the next couple of weeks. It's not like we're just doing them today. Today is just to focus on this particular concept. Okay? So because it is the first day, I would say, of straight FRQ practice, there are a couple of key ideas I want us to jot down as we're thinking about FRQs. They're things that I would say are common either across all 6 types of FRQs or maybe 2 or 3 of them. And then some that we're going to write down I would say are common ideas for specifically tabular data. Okay? So when it comes to tabular data, these ones are, I'd say, most commonly from your Unit 4, if you're wanting to go back and look in your Unit 4 notes. 4.6 in particular is where we looked at Riemann sums. Okay, so when it comes to tabular data FRQs, a lot of times students, when they see that they have one of these on their AP test, they will look through the parts, part A, B, C, or D, specifically looking for something about a left-hand Riemann sum, a right-hand, a midpoint, or a trapezoidal, and they'll walk through those ideas. You'll want to be careful with Riemann sums that you always watch for, I call them modifiers. So what that means is simply if you are ever, and you'll see some of these even today, if you're ever given the instruction to, for example, find the right-hand Riemann sum of, and then they have, say, 1/12 of some integral, make sure that that 1/12 does stay in your problem. And again, you'll see this in the context of problems in a bit, but this is a key idea that I want to make sure we are looking for. Okay? Other common ones when it comes to specifically tabular data are questions about over approximations or under approximations. And again, look in your 4.6 notes for both of these ideas. We practiced both of them at the time. We're going to be re-looking at them today. But they like asking that kind of question. Would this be an over approximation or would this be an under approximation? And for those, if you're looking at your 4.6 notes, you're going to want to look on the first page where we list our 4 approximations. We drew in what it would look like for a left-hand Riemann sum to be an over approximation or a left-hand Riemann sum to be an under approximation. And we did that for each of them, right-hand and trapezoidal and midpoint. Okay? Okay, the other common question I would say, or not, yeah, anyway, another common question would be something asking you to guarantee that some particular value exists. And so this would be the difference between IVT and MVT. Okay? IVT is in your Unit 1 notes. So IVT would have been in, let's see, I think it was 1.5. Let me pull up your notes at the time, double check that. I'm sorry, no, it would have been 1.4b. It was the very last thing in our 1.4b notes, if you're wanting to look this up. IVT, it is important with IVT that you articulate that the function is continuous, and that you articulate that you have bookends. So IVT, we actually brought this back during our particle motion unit. In the first table that we did, as we were walking through all the definitions in particle motion, and I asked you at one point, or asked the class as one of the questions we did up on the board, can we guarantee that the velocity equals 0 somewhere? And everyone said, oh yeah, of course, because they saw that there was a point where my velocity was positive, and there was a point where my velocity was negative, and the only way to go from positive to negative is to at some point pass through the value we're trying to guarantee, so in this case 0. And so IVT guarantees that a particular point exists as long as you are continuous and as long as you have what I call the bookends, 2 values on either side of the one you're trying to guarantee. MVT would have been unit 3, so MVT is 3.2 if you're wanting to look it up in your notes. It has to be continuous and differentiable. And then for MVT, MVT is used to guarantee that a slope exists. And so for MVT, you'd be looking for 2 points that when I do their rise over run, I get the slope I'm trying to guarantee. And we talked at the time, you can test any points you want. In 3.2, a lot of times we looked at a particular given interval, and so we started with that interval, the one that was provided, because a lot of times that's the one that will show you your slope exists. But then we discussed that, well, if those 2 points don't work, then technically speaking, you can use any 2 points as long as they lie on that interval, such that their rise over run gives you the slope you're trying to guarantee. And again, you're going to see both of these today. All of these ideas actually you're going to be seeing today. Okay, and then the last couple things I want us to jot down for ourselves, they are ones that I wouldn't say apply completely to tabular data. Well, actually, none of these apply completely to tabular data, but these are common tabular data ones. The other ones I'd say are just common in general, which is a reminder about what an integral is and what a derivative is. Okay, and we've looked at both of these over the last several weeks already, but I want us to write them down. An integral, as a reminder, is a total or an area, something accumulating, right? Some total quantity. Volume would be potentially an integral. We looked at a couple of different volumes within the context of Unit 6, both cross sections and solutive revolution. So any word that implies that totaling an overarching amount is an integral. And again, you'd want to watch for starting amounts. Because if I started at 7 and then I accumulated 15 over time, what I've got is technically 22. Right, so you'd want to make sure you continue to add that starting amount in. That's technically speaking the desired position formula back from Unit 7. Okay, and then derivative. A derivative, just as a reminder, is a rate or slope, rise over run if you're looking at a graph. So anything along those lines. So if you read any of those words, then that's going to be cueing some sort of derivative, and you'd be looking either for an already provided derivative, or you'd be looking to take a derivative, either of a function or doing, like I said, rise over run if you've got something there, maybe an f of b minus f of a over b minus a idea. Okay, and then I had a couple more. Okay, so 2 more. 2 more watch units. We talked about that in particle motion. There are a lot of times problems where the units themselves will be their own points. So watch for units. Make sure you write them no matter what. Make sure you write them no matter what. Because there are going to be problems them no matter what. Sorry, there are going to be problems where you might look at the problem and maybe get a little bit stuck, and so you've given it your best go, but you're like, I'm just not sure that my answer is the right answer. Well, still leave it. Make sure you leave nothing blank and attach the appropriate units to your answer, because it's entirely possible you might snag a point just through the units, right? And then the final thing here, which this one we actually haven't talked about since back in, I think this would have been Unit 2, if I remember correctly. We talked about it a little bit in related rates at the beginning of this second semester. But watch for comparison rates. So I'd say this one's probably going to be the newest point for today, outside of actually practicing FRQs. So watch for comparison rates. And what I mean by that is this, okay? Common questions, and again, it's not always tabular data. It could be potentially fall into any of our zones. You'll see things where, you know, the problem will talk about something going into maybe a pipe, and then something that then coming out of a pipe, and then you'll be asked to evaluate what's inside the pipe. Okay, well, if you imagine here's my pipe. Okay, if we have some quantity flowing into a pipe, and say that's I don't know, we'll just call it A of t, and then some quantity flowing out of the pipe, okay, what's inside the pipe would be potentially whatever you start with, right, if there is some sort of starting amount, but what's inside the pipe is that starting plus A of t, right, and maybe it's an integral of A of t or something like that, depends on what A of t is, and then minus B of t. A lot of times when you read these problems, and it'll say, you know, something's flowing into, something else is coming out of, and then students will miss that in the context of the problem, you might then be asked for what's inside the pipe, and they'll only consider one of the two quantities or one of the two functions, but both of these functions would be impacting what's inside the pipe, right? What's going in would be getting added to what's in the pipe, and what's coming out would be getting subtracted from what's inside the pipe. So the total would be kind of all three of these ideas: what was already there, what got added, and what got removed. So that's what I mean by watch for comparison rates as you're reading your problems. Okay? Okay, so now taking a look at these FRQs actually now in context. Let me switch over here. We are going to start with the first one that's actually on the PDF that I attached to Google Classroom, which is our 2017 one. On all the FRQs you'll be doing over the next several weeks, I will always indicate at the top of the FRQ whether it's calculator or non-calculator, so you know whether or not you can use that, and then what year this question is from. These answers are all out online for every single FRQ I'll be giving you, which means that technically speaking, people could copy them, and I acknowledge that that is something that could be happening, but this is where you need to make sure you own your practice here. I don't really care if you get 9 out of 9. Obviously that's fantastic, but remember those skewed percentages we've talked about over the last several weeks. The reality is not everyone's going to get 9 out of 9. You might get 4 out of 9 or 5 out of 9. And with each FRQ, the goal simply is to identify, can I get one more point next time? You don't need to get 100%. If you're able to, fantastic, but copying down an answer doesn't help. Okay? I give you the years that these come from so that you have that as a resource if you would like to double check things and you don't want to have to wait for me to release the answer key. So use that appropriately, right? Okay. Okay, so doing this one together here, unless you really want to pause it and try it on your own, kind of see how you do. But I'm going to walk through one just to kind of model my thought process as I look at tabular data Riemann sum problems. We have a tank has a height of 10 feet. So as I'm reading my FRQs, and I'm keeping in mind, remember that you have 15 minutes to just do this one FRQ, so you've got plenty of time, right? So as I read through it, I'm always annotating as I go, right? Underlining things, circling, drawing pictures if I feel like there's something that's coming to mind there. As I get into the problems, I'm writing down anything I can think of that might help me with the problem. Because honestly, there are some parts that even stump me every once in a while as I look at a new FRQ. And it's only through starting to write stuff down that something triggers mentally. You're like, oh, okay, let me try that. And then maybe that unlocks the answer to the problem. If nothing else, you want to make sure you have something written on every part. Don't ever leave it blank. Because who knows what kind of points you might snag just by writing applicable facts. Sometimes you can snag justification points or something like that, right? Okay, so as I read this, a tank has a height of 10 feet. So H equals 10. I'm going to go ahead and jot that down. Just in case I need it, I'm seeing that 10 feet there. Okay, the area of the horizontal cross section. Okay, so cross sections, I'm thinking 6.3. Cross sections in 6.3 were an integral with an area formula of some sort plugged into that integral. So the area of the horizontal cross section of the tank at height h feet is given by the function a. Okay, so a equals area. I'm going to go ahead and write that down. Right, the area is given by the function a, where a of h is measured in square feet. So then I always make sure I take a hard look at any sort of units provided, because if I'm asked for units later on, I want to make sure I'm writing the right ones. Okay. The function a is continuous. Okay, so continuous, I know now if I were to use IVT or MVT, both of which requires my function to be continuous, I can state that. And a decreases, so I know that a is going down. I know in the past I've had students who always like to kind of sketch the coordinates given in the table. And so you might like doing that, 0, 50.3, 2, 14.4, 5, 6.5, 10, 2.9. So kind of a rough sketch, that's A of t, so maybe you prefer to plot the points. And then selected values for A of h are given in the table above. Okay. A, we are going to use a left-hand Riemann sum. So this is what I said earlier. A lot of times students will look right for the Riemann sums because a lot of times you can snag a couple points. In this particular year, the Riemann sum aspect was worth 2 points. So it's a good place to start. Okay, so use a left-hand Riemann sum with 3 subintervals indicated by the data in the table. So I know I'm going all the way across the table to approximate the volume of the tank. 3 subintervals, so my subintervals are going to be 1, 2, 3. And then I'm going to indicate units of measure. Okay, and so I'm going to make sure that I put that in there as well. And we are indicating units of measure for our approximation of volume. So I actually already know what my units would be because I know what volumes units are. Think about volumes units. Okay, volume has units of cubic measurements. In this case, it would be cubic feet. So whatever answer I put down, whether I think it's right or wrong, I'm going to stick feet cubed at the back, hoping that maybe I snag a point. Okay? So left-hand Riemann sum, again 4.6 is where you can look at left-hand, right-hand, trapezoidal, and midpoint. Okay? We have our change in our base, which is 2. 2 to 5 is 3. 5 to 10 is 5. So my first subinterval here, it is 2 times my left-hand value, which in this case would be 50.3. Okay, second one, we have 3 times my left-hand value, which is 14.4. And then third, we have our 5 times my left-hand value, which is 6.5. And then you have a choice to make here. Remember with FRQs, you don't actually have to simplify anything at all. So even though this is a calculator one, so you might be tempted to want to plug this into your calculator and generate an answer, I would recommend not. Because again, you don't have to simplify. If you do take the time to plug that into your calculator, it will give you an answer of 176.3. And then again, make sure that your units are always tacked on the back. Okay, so again, this part here was worth 2 points total. 1 point was for the left-hand Riemann sum, which is what you've got here. 1 point was for the approximation, which if you simplified would be the answer. If you didn't simplify, this setup is both the left-hand Riemann sum and the approximation point. So you get 2 points for just this work. If you simplify incorrectly, so you plug it into your calculator wrong, you'll still get your left-hand Riemann sum point, but you're going to lose your answer point, right? So again, don't simplify. Okay, B. B is another common one, I would say, in terms of the AP test when it comes to tabular data, and so this is another one that students eventually start to look for. It might be a little bit weird the first couple of times you do it. Again, this is from 4.6 as well. It was the first part that we did in 4.6 in your notes. Okay, does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. Okay, well, my approximation in part A was a left-hand Riemann sum. And if you look in your 4.6 notes, we drew in what a left-hand Riemann sum would look like for a decreasing function and what a left-hand Riemann sum would look like for an increasing function. Okay, so for a decreasing function, a left-hand Riemann sum starting at the left and doing our rectangles, our left-hand Riemann sum for a decreasing function would be an over approximation. For an increasing function, the left-hand Riemann sum would be an under approximation if we started on the left and drew in our rectangle. And so the question becomes, well, what kind of function is this? What kind of function is A of h? And A of h is a decreasing function, right? And so that tells me that this would be an overestimate. And then it does say explain your reason. Explain always means words. Right? So why do we know overestimate? Because A of h is a decreasing function. And this particular one was only worth 1 point this year. 1 point for saying overestimate and having an appropriate reason. So if you did work through this differently or like on your own and you had a different explanation here and you're not sure if it works, feel free to snap a picture of it or email me or whatever you prefer. I'm more than happy to check your explanations, and that's true for all of these. If you ever pick a different route through the problem and want to verify that it's okay, contact me. I'm more than happy to support you in that. Okay? Okay, so we're sitting at 3 total points so far. We're on to part C. Part C says the area in square feet of the horizontal cross section. Okay, so there's that cross section word again. It's like that 6.3 integral of area here. Is modeled by the function given by f of h. Okay, so now I actually have an area formula. This right here is my area, right? Area square feet is modeled by the function f. Based on this model then, find the volume. Okay, so this is pretty much exactly out of 6.3. What makes this one a little bit tricky is the fact that we're used to having to kind of come up with our own area formula, right? Identifying whether it's a square or an equilateral triangle or whatever happens to be. In this one, they actually quote unquote help you out and give you your area formula. But like I said, it's a little bit different than what we are used to seeing, and that is going to be the case as you continue through your FRQs. They're going to ask some of these extension pieces. Okay. The other reason, though, that we know that this is going to be an integral, besides that they ask for volume and that connects to 6.3, is that is what an integral is. An integral is a total. It's an area. It's an accumulation of something. And so in this case, I'm finding my volume. Okay, and so volume here is going to be 0 to, let's see, what do we find the volume of? Volume of the tank. And the tank has goes all the way up to 10 feet. So we're going 0 to 10 of my f of h, which is my area formula. That's what we do with a cross section, right? Integral of area. There's my integral of my area. Okay, and then this one is, I should say dh, not dt. This one is a calculator question, so you would now pick up your calculator, you'd hit Math 9 or F5 for my 89s, or depending on what calculator you have, however it is that you calculate an integral, you would plug this in, and you should get 101.3253, I think it's 34338 or something like that, but remember, your answers only have to be accurate to 3 decimal places, so you should get 101.325. If you have plugged it in and didn't just get that, again, contact me. I'm more than happy to either make a separate video plugging into your calculator if you would like, so you can check that, or you can take a picture of your calculator and send it to me, or whatever the case may be. But that would be 101.325 is what you should get. And this was worth 2 points. One was for your integral, setting it up. And then one is for the answer, which is, again, kind of funny because it's a calculator one, so as long as you've plugged it in correctly, you should get that second point. Which kind of brings me to another thing that you'll hear me say a couple of times as we continue in FRQs. If you don't know what to do, either take a derivative or take an integral. If you're looking at, especially with a problem like this, if you're looking at something where you've got an equation, either take a derivative or take an integral if you're completely stuck. And so that is where the definitions are going to come in mind, because if you are completely stuck, you'd be looking for something that rings similar to these words for an integral and similar to these words here for a derivative. And so sometimes it is a matter of like, well, I don't know what to do, but I see volume, and volume kind of sounds like a total, so maybe I'll take an integral and hope for the best. And in this case, if you had just randomly taken the integral and plugged in, even if you weren't sure why it worked, although hopefully now we know why, but if you weren't sure why it worked, plug something in. Don't leave it blank, right? You could snag 2 points from having taken this integral correctly, and you had your calculator, so you don't have to do it by hand. Okay, and then final thing here, indicate units of measure. We found the volume of the tank, indicate units of measure, so volume again would be feet cubed. 101.325 feet cubed. Okay, last one, which in my opinion of the four is the trickiest for this particular year. But I want us to talk about one point that we should have been able to snag after reading D. And then we'll take a look at the whole thing. D says water is pumped into the tank. Okay? So pumped into, I'm thinking some sort of positive idea, right? Tank, here's my tank. It's filling up with water as water's being pumped in. When the height of the water is 5 feet, so 5 feet for my height of water there. The height is increasing, so again, thinking some sort of positive idea, at the rate, so that's a ddt, and in this case, this is the height is increasing, so dh dt, at a rate of 0.26 feet per minute, or foot per minute. This, by the way, is in related rates, if you're wanting to know where this kind of problem is from, which is the very beginning of second semester. Using the model from part C, so our f of h here, find the rate, so we're finding a ddt, in this case at which the volume, so dv dt of the water, is changing with respect to time when the height of the water is 5 feet. So again, h is 5, and then indicate units of measure. Okay? So like I said, this one in my opinion is one that I think is the trickiest, but here's the point that I want us to have made sure we snagged at the end of this problem. Indicate units of measure. I'm finding dv dt, volume over time. Okay, so what would volumes units be? Okay, we've written this one a couple of times. Volumes units would be feet cubed. And times units? Times units would be minute. One of the points this year for 2017 on this problem was having appropriate units in A, C, and D. So even if your answers were completely wrong, but you had feet cubed on A, feet cubed on C, and feet cubed per minute on D, because you recognized A, we were finding volume, C, we were finding volume, and D, we were finding the rate of change of volume, and could write those units down, you got a point for having the correct units in A, C, and D. But you did have to have all three of them. So again, if you had left D blank, you would have just lost that point. Don't ever leave a problem blank. Look for the information you can write down. Slow down, breathe, break the problem down. Okay? Okay, now actually solving this one then. We are wanting to find the rate of change of volume. Well, volume, remember, was our integral from say 0 to, and then some height. My tank, it was 10 feet. I don't know what my water is going to be, of my f function. Okay. And so then taking the derivative, dv dt, we take our derivative using whatever derivative rule we would need. In this particular case, we're taking the derivative of an integral, which comes out of 4.4b. Derivative of an integral is second fundamental theorem of calculus. And so we're going to plug in our upper, f of h, times the derivative of my upper. Derivative of h would be 1, and then dh dt, because I just took the derivative of h. Minus, plug in the lower, f of 0, times the derivative of my lower, which is 0. And so my dv dt here would be f of h dh dt. Okay, you got 2 points for having the dv dt correct. Your final point then for this problem, because again this problem was worth 3 points here. 1 for units in A, C, and D. Okay. Your final point came from your answer, which is finding that volume at 5 feet, when the height is 5 feet, I should say. And so my dv dt at h equals 5 feet is, and then it's a calculator one, so you can use your calculator as much or as little as you would like. We need to plug in our 5 feet here, and so if you wanted to, you could plug in 50.3 e to the 0.2 times 5 plus 5, plugging your 5 into your f function. And you could get that value and then multiply it by your dh dt, which is 0.26. Or, because you don't have to simplify anything, you could write that out. 50.3 divided by e to the 0.2 times 5 plus 5 times 0.26. Okay. If you did take the time to plug that into your calculator, you should get about 1.694. I'm plugging that into your calculator there. Okay? Okay, so there's your first tabular data, and I'm sorry, I know I went kind of long through that one, but I was trying to break it down with different thought processes. Each one that we go through, I'll go a little bit quicker, but I am still going to take my time, so feel free to fast forward videos to the parts of the problems that you need to see done. I'm going to still break it down piece by piece. And again, with each successive, or each one after this, your goal is to say, can I get one more point than I did last time? Your goal, I mean, if your goal is to get 100%, great, but ultimately speaking, that's not really our goal. Our goal is to get into those ranges that we are shooting for here. So identify what's one more point I could get next time, what's one more thing I could do differently the next time I see a tabular data problem. Okay? Okay, the next one I'm going to be doing is the 2014 one, which is actually the third FRQ that's been uploaded to Google Classroom. So it's the one that talks about a train. So non-calculator 2014 is on the third page. Okay? If you would like to pause the video now and restart it when you're ready to kind of see how you did with the second one, you're more than welcome to do so. If you'd like to watch one more with me and then maybe pause the video on the next one, that would work too. Okay, let me pull up the rubric for this one, make sure that I get my points in the right spots as we're talking through it. Okay, 2014. So we have a train A runs back and forth on an east-west section of railroad track. So I'm definitely a picture person myself, although I'm not an artist. So here's my train A traveling east-west. Train A's velocity measured in meters per minute. So I'm taking a look here at my units, meters per minute, minutes, okay, making sure I'm taking note of those, is given by the differentiable function v sub a of t, where time t is measured in minutes. Selected values for v sub a of t are given in the table above. Okay? So I didn't actually pull a whole lot from my read through there of my paragraph. I always like kind of drawing a little bit of a picture, especially when there's something there that is somewhat real world in being described. Okay, so A, we have find the average acceleration. Okay, so I'm going to go ahead and pause here. I know average acceleration. We actually just did this in Unit 7, but this originally is in your 4.4b notes. But then again is in, we'll call it particle motion, your particle motion notes if you want to look at those. Average is 1 over b minus a times the integral from a to b. In this case, it's going to be average acceleration. And so I'm going to be putting acceleration in there. Okay. My a and my b for this problem are 2 to 8. So 1 over b minus a times the integral from a to b. And then I'm going to go ahead and evaluate this. Okay. So 1 over 8 minus 2 is 1/6. The integral of acceleration is velocity. That's definitely from your particle motion notes. And then plugging in your upper, we have velocity of 8, v of 8, which is here. V of 8 is negative 120. Minus, plugging in my lower, v of 2, which is 100. Okay. And then you have a choice to make. You can simplify this if you would like, but you don't have to. Remember, FRQs, you don't have to simplify anything. You have to evaluate it. We can't leave it here. This is unevaluated. But we don't have to simplify anything. I don't even have to make this 1/6. I could leave it as 1 over 8 minus 2 if I wanted to. And so if you are at all sitting there going, I'm not sure I'd simplify correctly, then leave it. If you do simplify, you should get either negative 220 over 6 or negative 110 over 3. And then I always recommend writing down units, even though they didn't tell you to. You never know. This is average acceleration, and acceleration's units are distance, which is meters, per time squared. Now I will go ahead and spoil it a little bit and say that this year the units did not help you much with part A here, but it's good to throw them in just in case. This problem was only worth 1 point for your answer, which is why I would recommend not simplifying. This part's only worth 1 point anyway. Don't waste your time and potentially lose the 1 point you've earned. Okay? Look in here. Okay, part B. Part B says, do the data points, or does the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time between 5 and 8. So 5 and 8 are here to here. Does the data support that at some point the velocity would have to be negative 100? Okay, well, if you take a look here, at 5, my velocity was 40. At 8, my velocity was negative 120. And so, yeah, at some point I'd have to have my velocity equal negative 100, only because, again, careful with this, because this is IVT. This is how we guarantee a point exists. This is 1.4, if you're wanting to know where this comes from. So let me write that down, 1.4b in your notes. Only because to guarantee a point exists, we have to be continuous, which our function is continuous, so we're good to go, and we have to have bookends. Okay? And so then I'm going to go ahead and write that down. Yes, because my function is continuous, and you don't have to say differentiable, but I'm going to, because that's technically what they tell us our function is differentiable. So I'm going to write it just to say why I know it's continuous, where it comes from, right? So velocity is continuous / differentiable. And then something about negative 100 being between your velocity at t equals 5 and your velocity at t equals 8. So when you look online at the rubric College Board release, they wrote that as an inequality, which it actually is very similar to how I wrote it in 1.4b. I tend to always write it with my lower number first. So in this case, that would be my 8. Stating what that equals, which is a negative 120, and then stating that negative 100 is between those two values. And I don't always write it like that. Like we talked about in 1.4b, there are other ways of articulating that your negative 100 in this case is between your two values. But you would want to have those two criteria. Again, for IVT, guaranteeing that a point exists. This guarantees a point exists. You have to state your continuous, and you have to state what your bookends are. Okay? This one was worth 2 points. 2 points for correctly articulating yes with both of those conditions. And your other point came from recognizing in some way, shape, or form, and so even if you had not gotten the continuous down, you could have snagged this point, came from recognizing in some way, shape, or form that negative 100 lies between negative 120 and 40. And so potentially speaking, you could have snagged that point by writing that out, writing your thought process as you looked at this table for how you knew that negative 100 would definitely exist. Okay? Okay, C, we have at time t equals 2, train A's position is 300 meters east. Okay, so I've got here some position of my train at t equals 2. And the train is moving east. Write an expression involving an integral. Okay, so write an expression involving an integral that gives the position. Okay, well this comes out of particle motion, technically speaking. An expression that involves an integral that gives a position is the desired position formula. And then we are going to use that, at time t equals 12, we're going to use that expression with a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time t equals 12. Okay, so let's go ahead and start with our expression here. My train starts at 300, that's my given position. My given time is 2, and the time I'm trying to find for this one is 12. If you're looking in your particle motion notes, this is on the back side of the first page of your particle motion. It would have been number 6, I believe, 6 or 7 on the back side. Okay, and then using a trapezoidal to approximate our position. So we have our 300 plus, and then we are doing 2 to 12. So 3 subintervals with our trapezoidal here. 2 to 12 is our distance. So we have 1, 2, 3 subintervals getting me from 2 to 12. So this is 3 for 2 to 5, 3 for 5 to 8, and 4 for 8 to 12. Trapezoidals are also in 4.6. Okay, trapezoidals are 1/2. You'll still have that change. So for my first subinterval, that change is 3. And then you use not the left, not the right, but both. So not just the 100, not just the 40, but both the 100 and 40. And then you repeat that process for the other 2 subintervals. 1/2, the change, which is again 3, And then not the left, not the right, but both. Not the 40, not the negative 120, but both of them. 40 and negative 120. And last one, 1/2. Change for this one is 4. And then not the negative 120, not the negative 150, but both the negative 120 and the negative 150. Okay? And then same choice, you can simplify if you want, but remember, non-calculator, so you'd need to make sure you simplified correctly. You'd lose your point, potentially speaking, if you simplified incorrectly. This particular problem was worth 3 points. 1 point came from your position expression, right? 1 came from your trapezoidal sum, so just this piece right in here, my 3 subintervals trapezoidal, and 1 came from my answer. So to get my answer, I would have had to have this 300 out front for this particular one. Okay. Okay, last but not least, we have part D. A second train, train B, travels north from the origin station. Okay, so I'm going to go ahead and draw that in my non-artistic way. So B is traveling north. At time t, the velocity of train B is given by this function. So I've got a velocity function there. And at time t equals 2, the train is 400 meters north. So now I've got a position here for my B, 400 meters north of the station. Find the rate, so this is d dt, at which the distance between train A and B, so I'm going to call that d dt, is changing at time t equals 2. So this is another related rate, beginning of this second semester. Okay? Okay, so to find d dt, I need to find out what that distance is. So what is the distance between train A and B? Well, here's B. A, remember, was going east-west. And so the distance between them would be d squared equals a squared plus b squared. Right? Pythagorean theorem, it's a right triangle. It's kind of like the ladder problems, sort of. Okay? So derivative, our derivative of d squared would be 2d, and then dt, because I just took the derivative of d. A, we'd have 2a, dA dt, and B, I'd have 2b, or not to be, no, 2b dB dt. Okay? And so then plugging in our values here, the distance between my two trains, well, A, remember, was at 300 meters from part C, B's at 400 meters, and so the distance between those two, this is a 3, 4, 5 triangle, so you might be able to say immediately that's 500, or maybe you use Pythagorean theorem to figure out, well, if A is 300 and B is 400, what would D be? So you do 300 squared plus 400 squared equals D squared, and solve for D. Okay. Don't know d dt, that's what I'm trying to solve for. My A was, again, 300. My B was 400. My dA dt, my velocity at time t equals 2, was 100. Here's my dA dt. Remember, velocity is a derivative. Okay. My dB dt, my velocity of B, is this function here. Remember, non-calculator, so you can take the time to evaluate that if you want, or you could simply plug in your 2 and call it good. And so then solving for d dt would be dividing this 2 times 500 over to the other side. And again, one more time, you can simplify if you'd like, but it earns you no extra points. And if you simplify incorrectly, you now have lost your answer point. So I would recommend only simplify as far as you need to be able to accurately finish the problem. And so I would recommend leaving it like this. Okay, and so then this one was also worth 3 total points. 2 came from being able to take your derivative, so they called it the implicit differentiation of distance relationship. And then 1 came from plugging in and solving your problems here. So you got 1 for all of this answer work. 2 came from the derivative process. Yeah, and then that's 2014. I was double checking that adds up to 9, but we got all our points on. Okay? Okay, so my recommendation now is if you haven't already, pause the video, try the next one on your own. We're going to do 2013 next. Okay? Try it on your own. And again, your goal is to not necessarily get 100%. Your goal is to get 1 more point than you did the time before. Each time, identify 1 more thing. You can get a little bit stronger on your belt because we are not done with tabular data problems today. Right? Okay, go ahead and pause the video, give this one a shot, restart it when you're ready. Okay, so 2013, we are looking at a non-calculator one here. It says hot water is dripping through a coffee maker, filling a large cup with coffee. So again, I'm always drawer myself, not fancy drawings, but just something to make sure I'm kind of picturing what's being talked about. So there's my hot water dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t, such that t is between 0 and 6, so we want to take a hard look at those bounds, is given by a differentiable function c, where t is measured in minutes. And so again, take a look at my units here. Minutes, ounces. Selected values of t, c of t measured in ounces, like we talked about earlier, are given in the table above. C again is what's inside the cup. So I'm going to put C of t in my cup to remind myself that's what C is representing. Okay? So, part A, use the data in the table to approximate C prime of 3.5. Show the computations that lead to your answer and indicate units of measure. Okay? So, in your notes, this one originally comes out of Unit 2. We would have done a little bit more with it in Unit 3, and then we would have done problems like this if you wrote them down in your particle motion packet. So at the very first page, when we were walking through all the definitions, there's a table right in the middle of that page, and we paused at the time and we wrote down different other examples that could be asked about that table, and up on the board we would have done one together where I had you approximate a derivative using the table, and then one that I gave for you guys to do with your partner. And I know I had some people who didn't write it down, so this might be your time to jot this idea down because it is a common one. To approximate a derivative, right, c prime of 3.5, remember a derivative is a rate or a slope or a rise over run, something like that. Okay, to approximate a derivative, we would be looking at some type of slope. And so I remember when we did this one in class, some people plotted their points so that they could do a rise over run. 3.5, by the way, would be right in here, so that's where I'm approximating my slope at. Other people did f of b minus f of a over b minus a, did the change in y over the change in x, I should say. So whichever one you prefer, you should get something along these lines, that c prime of 3.5 is approximately either 12.8 minus 11.2 over 4 minus 3, or 11.2 minus 12.8 over 3 minus 4. Or, if you do want to simplify, you can. Again, I don't recommend it. But if you simplify, this would simplify down to 1.6. Okay? And then indicate units of measure. So we are finding the derivative of C. Well, C was my ounces. So c is like position here. If I took its derivative, that would be like velocity, right? And velocity has units of distance, so ounces over time, which would be minutes. Okay. This particular problem was, let's see, 2 points this year. 1 point came from your answer, your approximation, the 1.6 value here, and 1 point came from the units, separate from the answer. So even if you got stuck on the answer, but you could write down appropriate units for C prime, you could still grab a point for this particular year, this particular problem. Okay? Okay, B, we have, is there a time t between 2 and 4 such that C prime equals 2? Justify your answer. Now, justify, when you see justify, means words or work, whichever is most applicable and whichever is thorough. Right? For me, I usually go with both unless I am sure my work leaves no room for any sort of doubt when it comes to supporting my answer. Okay? So is there a time between t and 4 such that C prime equals 2? Okay? Well, this is our MVT. MVT again is unit 3. So 3.2 if you're wanting to look in your notes. Okay? Requires you to be continuous and differentiable, which our function is, differentiable function C. Okay? And then if you could say that you're continuous and differentiable and you can find 2 points, B and A, and again, any 2 points on your interval will work, but if you can find 2 points who give you a slope that you're trying to guarantee, then you can guarantee that slope exists. So in this case, I'm trying to guarantee that I have somewhere a slope or a derivative of 2. And so if I can find any 2 points on this interval, 2 to 4, that give me a derivative or a slope of 2, then using MVT I can say, yes, it exists, right? So for me, like I talked about in 3.2 when we did this one, I always start with the 2 points given. So I always start with 2 and 4 to test that. But if 2 and 4 don't give me a slope of 2, then maybe I try 2 and 3 next. And if that still doesn't give me a slope of 2, then I try 3 and 4. Or any other combination that sits in the interval given, in this case 2 to 4. Okay, but let's go ahead and try 2 to 4 first. So f of b minus f of a all over b minus a. Okay, well c of 4 in this particular case was 12.8. C of 2 in this case was 8.8. Over 4 minus 2, which 12.8 minus 8.8 is 4, 4 minus 2 is 2, and 4 divided by 2 is 2. And so yes, I can guarantee that the slope exists. So is there a time? Yes, because C of t is differentiable. And, right, so the 2 things you need for MVT, continuous differentiable, and f of b minus f of a or b minus a, you need to show that you have found 2 points that give you the slope you're trying to prove. So in this case, actually I'm going to say c, not f. C of 4 minus c of 2 over 4 minus 2 gives me that slope. Okay, this one was worth 2 points. 1 point came from your articulation of your answer, which means yes, you did need to have this differentiable continuous. That's part of MVT. And then your f of b minus f of a piece. The second point came from simply finding that location, so testing your values until you find which one gives me, in this case, a slope of 2. So again, if 4 and 2 hadn't worked, I might have tried 2 and 3 next, or 3 and 4, until I found the slope I'm trying to guarantee exists somewhere on my interval. Okay? Okay, C, we are coming out of 4.6 initially speaking, although a little piece of this is also going to come from 4.4b as we get into the problem. C says use a midpoint sum, so that's the 4.6, with 3 subintervals of equal length indicated by the data in the table. Okay, let me pause. So here's my data in my table, 3 intervals of equal length. Well, the only way to get 3 subintervals of equal length would be to go 0 to 2, 2 to 4, 4 to 6. I now have 3 subintervals of equal length for my table. To approximate the value of 1/6 of my integral. Okay, so I'm going to go ahead and pause here. Let's go ahead and approximate that value. So 1/6 of my integral. Midpoint. Okay, midpoint sum would be your change again. Remember that change is in every single one of your approximations. So 0 to 2 is a change of 2. 2 to 4 is a change of 2. 4 to 6 is a change of 2, which it should be. Remember, 3 subintervals of equal length. Those should all be the same. So we still have that change. My first subinterval is 2 times, for midpoint, not the left, not the right, but the middle, 5.3. I mentioned back in 4.6 when we were doing this that I don't have a ton of examples of midpoint. This is one of the ones that I've got here. And so as we walk through this, I would definitely make sure that I was writing this down. I would say left-hand, right-hand trapezoidal tend to show up a little bit more, okay? Typically speaking. Again, can't speak to this year, so it's good that we're reviewing them. I tried to get kind of one of each idea into today's notes, okay? Second subinterval, we have our change. 2 to 4 is a distance of 2. And then again, not your left, 8.8, not your right, 12.8, but your middle, 11.2. And then third subinterval, 2 for your change, not the left, not the right, but the middle, 13.8. And then again, you can simplify if you want, but I wouldn't, right? You have no extra points and you have no calculator, so I really wouldn't recommend doing that. We are not quite done with this problem, but I want to pause here and say at this point you have earned 2 points. 1 comes from the midpoint approximation in here, and 1 comes from your answer. Now, if you leave it like this, you've earned that answer point as well. So you've earned 2 points from what we have here. You lose that answer point one of 2 ways for this problem. 1, if you forget the 1/6 out front. At the very beginning here, we wrote down Riemann sums, watch for modifiers. That 1/6 is what I mean by a modifier. We're modifying that integral slightly by multiplying it by 1/6. The other way you would lose it is if you had this written, but then you simplified it correctly. You would now lose your answer point, even though you'd still get your midpoint approximation. Okay? There is one more point available for this problem, which is the last sentence here. Using correct units, okay, so we've just totaled up the amount in our cup, right? So to approximate the value, so we've totaled it up, so this would be ounces for units here. Okay. Explain the meaning of this 1/6, 0 to 6 of C of t in the context of the problem. And so when it comes to explaining meanings, there's lots of ways of doing this. First rule of thumb, make sure that any time intervals, or especially for one that specifies units, but make sure any time intervals and units are part of your explanation. And so in this case, my time intervals are going to be 0 to 6. So I'm going to make sure that that's part of it, and specifically 0 minutes to 6 minutes as I'm explaining what's happening here. The other thing I tend to recommend is to go piece by piece through the equation and to write out what that mathematical term means in kind of English verbiage in terms of our equations. So I'm going to demonstrate what I mean by that with this problem here. Okay, so I always tend to start with rewriting my equation. 1/6, 0 to 6 of C of t dt is, and then I work my way through. Okay, so what is 1/6? Well, what type of equation have we seen a fraction out front of an integral like that on? Okay, well that's that 4.4b element that I articulated earlier. Okay, that's average. That's 1 over b minus a out here. 6 and 0 is the average. And then I work my way through average what? So remember, like average acceleration, we do this and we put acceleration in. So what is C of t? This is the average. And C is amount of coffee in ounces in the cup from, and then my time interval, t equals 0 minutes to t equals 6 minutes. Your last point comes from that articulation, that interpretation. Okay. By the way, if you did simplify this down, if I remember correctly, let me double check. I think you get 10.1. Yes, yeah, you do get 10.1 if you were to simplify this, but again, I wouldn't. Leave it as is. You're good to go. Okay, D, we have the amount of coffee in the cup in ounces is modeled by B of t equals 16 minus 16 e to the negative 0.4 t. Using this model, find the rate. So we're looking at some sort of ddt, at which the amount of coffee in the cup is changing when t equals 5. Well, the amount of coffee in the cup is b, so the rate at which the amount of coffee would be dB dt derivative. Okay, this is non-calculator, so we would have to be able to do this by hand. So to take the derivative of my b here requires the e rule, which is from 5.4, I think it was 5.4a if I remember correctly, but it's somewhere in your 5.4 notes. Okay, and if you can't find it, send me an email. I'll look it up and send you a picture of it. It's also on your yellow sheet, integral of e. I'm sorry, derivative of e. Okay, so derivative here, dB dt equals, derivative of 16 is 0. The negative 16 is a coefficient. E to the u is e to the u times u prime. My u prime would be negative 0.4. And again, you can simplify that if you want. I wouldn't. You don't have to. And then we're finding that derivative when t equals 5. And so plugging in 5, I'd leave it alone. This is 2 points. This problem, one came from being able to accurately take the derivative of that function, and one came from plugging 5 in. If you did mess up slightly on the derivative, you could still, by the way, get this second point, even if you didn't get the derivative correct, as long as you didn't oversimplify the problem. And that's true for all of these. Remember, we talked about that when we were grading our slope fields FRQs back in Unit 7. If you make a mistake initially, you can still continue to get points if the rest of your work reflects that mistake, as long as you haven't oversimplified the problem. Okay? Okay, one more here. Again, if you have not yet paused the video, I would highly recommend doing that. Practice at least one of these on your own, because again, you're going to have to continue to practice these within your homework over the next several weeks. Okay? Calculator 2016, this is on the second page of what was uploaded to Google Classroom. Okay, we have water is pumped into a tank at a rate, so I'm thinking some sort of ddt, modeled by W of t, so I know W of t is a derivative there, liters per hour, so recognizing some units there. I've got a time interval, 0 to 8, where t is measured in hours. And water is being pumped into the tank. So again, I'm a picture person, so there's my W of t going into the tank. Water is removed from the tank. Okay, so I'm going to go ahead and do this guy. Water is removed from the tank at a rate modeled by R of t, where R is differentiable and decreasing. Okay, so I'm seeing some kind of keywords there. This is, at some point, needs to start making you think like maybe an IVT or an MVT problem somewhere in here. You'd maybe be looking for it. It's not always there, but maybe you're starting to look for that. Decreasing, again, we talked about decreasing going down, or maybe you want to sketch the points out for yourself, something like that. If you wanted to actually plot the points to see your decreasing function, you could. Also 0 to 8. Selected values of RT are shown in the table above, and then last sentence, at time t equals 0, there are 50,000 liters of water in the tank. So I'm starting here with 50,000 liters in my tank. Okay, A, estimate R prime of 2, show the work that leads to your answer, indicate units of measure. Okay, so we've already done one of these, so here's a second one for you. Again, pause the video, try it on your own if you haven't already. 2 is right here between 1 and 3 to estimate a derivative. We're doing slope or rise over run. So either 1190 minus 950 over 1 minus 3 or 950 minus 1190 over 3 minus 1, whichever one you prefer. If you do simplify, is a calculator one, so you might choose to. Again, I still don't recommend it, right? It's a waste of time. Even though you've got your calculator to do the work for you, those seconds that you take plugging into your calculator are precious, right? Don't do it. But if you did take the time to plug that into your calculator, you would get an answer of negative 120. Okay? And then indicating units of measure, in this case, my R was liters per hour, so R is kind of like velocity here. R prime then would be the derivative of velocity or acceleration, and so my units here would be liters per hour squared. This problem was worth 2 points, 1 for the answer, 1 for the units. If you got the answer wrong but had appropriate units, you still got the units point. Okay? Okay, 2, use a left Riemann sum with 4 subintervals indicated by the table. Okay, so I'm going to go ahead and pause. 4 subintervals, 1, 2, 3, 4. Distance of 1, distance of 2, distance of 3, distance of 2 across my subintervals there. To estimate the total amount of water removed from the tank during the 8 hours. And then, is this an over or an under approximation of the total amount of water removed? Give a reason for your answer. Okay, so first up we have our left-hand Riemann sum to approximate my total being removed here. Remember, total is an integral. Okay, that's what an integral is. You don't actually have to have this written down if you don't want to, but I'm going to. Left hand then, we have our first distance here, which is 1, times the left hand side, which is 1340. Second subinterval, distance of 2, times the left hand, 1190. Third subinterval, distance of 3, times the left hand, 950. And fourth subinterval, distance of 2, times the left hand, which is 740. It is a calculator one, so maybe use your calculator, maybe you don't. Again, I wouldn't. This is 8050 if you did end up simplifying it, 8050, but I'd leave it alone. Okay? So far you've earned 2 points, 1 for your left-hand Riemann sum, which is what you just wrote out here, and 1 for your answer. Which again, because you don't have to simplify, this gets you both points. If you do simplify, you'd have to get 8050 to get that second point. If you don't get 8050, you'll still get the left-hand Riemann sum point, but you'll now have lost the answer point. Okay, there is one more point available in this problem. That last point comes from the last 2 sentences. Is this an overestimate or an underestimate of the total amount of water removed? So again, this is from 4.6 in your notes. Even drew these in on the prior problem, 2017. We looked at, even with a left-hand Riemann sum, what that looked like. Although again, all of them are drawn into your 4.6 notes. A left-hand Riemann sum for a decreasing function would be an over approximation. For an increasing function, it would be an under approximation. So what is this R of t? This R of t is a decreasing function, and so that would tell me that this is an overestimate. If I drew in that left-hand Riemann sum, it would definitely be above my function there. Okay, so overestimate, because R of t is a decreasing function. Okay? C, use your answer from part B to find an estimate of total amount of water in the tank to the nearest liter at the end of 8 hours. So these last two parts are in my opinion, the more challenging ones of the four. So C and D, I think, are a little bit more challenging than A and B. A and B, once you get the hang of them, are pretty straightforward. You've seen even already a couple of them today, and you're going to continue to see them. And just between A and B, you've got 5 points. In years past, that would put you pretty solidly in the 4 range. I can't speak to this year. This year potentially might be a little bit different, but in years past, that would be put you in the 4 range. So C and D are where you're going to be looking to grab a couple more points to either solidify that 4 or potentially to bump you up into the 5 range. Okay? So C, use your answer from part B to find an estimate of the total amount of water. Okay, so total, I'm thinking some sort of integral, in the tank to the nearest liter at the end of 8 hours. Okay, the reason I underline that in the tank is because of this last one that we wrote at the very beginning of this video, which is watch for comparison rates. And I described a pipe, and A going into the pipe and B coming out of the pipe. And so what's inside the pipe is your starting plus what goes in minus what comes out. The reason that's important here is because it's very tempting to want to just use the W of t. People see total, they do integral from 0 to 8 of W of t, and they call it good, but W of t is just what's going into the tank. There was already 50,000 in there, and R of t was getting subtracted away, right? There are 3 things impacting what's inside of my tank here. And so as we are approximating our total amount in the tank, we need to make sure we say, well, there are initially 50,000 liters already in there. And then W of t is going in. And R of t is coming out. Okay, and so then you have your calculator. So you have a couple of options here. You could pick up your calculator, do 0 to 8, plug in your W of t, and get its answer. Okay, and you should get around 7,836.195325, somewhere in that zone. And then you could choose to now plug into your calculator and get this value. Okay. Or you could rewrite this entire thing behind the minus. Just make sure there are either parentheses around it or distribute the negative in. Or this is a strategy where if you're ever wanting to use a long number that you've already written down before and you don't have to keep rewriting it every time and maybe accidentally write it wrong, you can always set this equal to some letter, some variable, and so then you can use that variable. Just make sure that whatever variable you use, it hasn't been used at all in your problem already. And so I always go with ones that are, myself, a little bit more out there, ones that maybe are not as frequently used, like M, for example. Okay, and so then I'm going to write 50,000 plus what I got from my calculator, which is around 7,836.19532, and then minus M, so that I don't have to rewrite all of that, and because, like I said, I would not take the time to plug this in and get the 8050 that it equals. If you want to, you can, then you can write minus 8050, and then you could plug all this into your calculator if you want, but again, it's kind of a waste of time. Your final answer does need to be accurate to the nearest liter, and so my final answer would end up being all of these without the decimals, or here, let me write that, 50,000 plus 7836 minus my m, or if you plugged that in, your 49,786, whichever one you prefer. Okay? This particular problem is worth, let me check this, I think it was 2 points. Yes, was worth 2 points for this particular one. Whoops. Just double checking my addition here. I typed it in wrong. Yeah, 49,786. I was double checking that. I did, in fact, remember the answer correctly. Okay, so this one was worth 2 points. One was for the integral piece. So if you had, for some reason, forgotten about the starting amount in the tank and what was getting removed from the tank, but you had seen, oh, total, I know how to do a total. A total is an integral, and so then I integrate the one function I've actually got, which is w of t for 8 hours, and maybe again you aren't sure, and so you put something down. You take a derivative, you take an integral, whatever it seems like might be most applicable. You still would have gotten 1 point just for evaluating that piece. The second point came from your answer, which again, I wrote my answer like this on my answer key, but you could write 49,786 if you wanted. Okay? And then last 2 points come from part D. Part D is kind of funny here. For 0 to 8, t between 0 and 8, is there a time t when the rate at which the water is pumped into the tank, so rate at which water is pumped into the tank, this is my w of t, is the same as, so what does it mean to be same as? Equal. The rate at which water is removed from the tank, which was my r of t. Explain why or why not. And so what they're asking me is there any place where r of t equals w of t? Okay. Your first point in this one comes from considers w of t minus r of t. The reason you might consider that is for r of t to equal w of t, it means that if I subtracted one of them over to the other side, and so that could be either subtracting the w of t over with the r of t, or the r of t over with the w of t, one of the two, or here, they would have to equal 0, right? Like to have two things equal each other, if I subtracted them, they'd have to equal 0. And so you got a point for just considering that fact, considering what w of t minus r of t might equal. And then your second point came from finding an answer with a solution, which is there any place where this is true? Well, on 0 to 8, if I plugged in, and again you could do either one, but say I plugged in w of 0 minus r of 0, okay? My w of 0, using my calculator and plugging that in, would give me 2,000 e to the 0, which is 2,000, minus my r of 0, so my 2,000, minus my r of 0, which is 1340, is 660, or some positive value there. Okay? My w of 8 minus my r of 8, which is the other end of my interval, w of 8, if I take my calculator and plug that in, I don't remember what we get, 2,000 e to the negative 64 over 20. I'd get 81.52440796 minus my r of 8. My r of 8 in this particular case is 700. Okay, would give me negative 618.475592. Okay? I know, therefore, that my w of t minus r of t, or my r of t minus w of t, has to equal 0 because I was originally at 660, which is some positive number, and then I was at negative 618, which is some negative number. And so I had to have passed through 0 there. And so your second point, again, 1 point comes from considering r of t minus w of t. The second point, which again I think is the hardest one to earn of this particular FRQ, comes from articulating all of that, which is that because your functions are continuous, right? So yes, because W of t minus R of t is continuous or differentiable. And then articulating your bookends. So something about W of 8 minus R of 8 equaling negative 618.475592, which is less than 0, which is less than 660, which is what W of 0 minus R of 0 equals. Okay? Okay, so those are our tabular data and Riemann sums. Again, you are going to continue to practice these. We are not done with tabular data. It's just to get us started to think about some of these older concepts. Because again, some of these come back from first semester. Some of them are here in second semester. That is what's going to be a little bit challenging about these FRQs. It's why we're going to practice so many of them, is they are usually pulled from a variety of our units. The exceptions being the ones we have already looked at, but these 3 new ones, they aren't going to come just from Unit 3 or just from Unit 4. You can have a little piece from Unit 4, a little piece from particle motion, a little piece from Unit 1. And so you're going to need to make sure you're looking in your notes at each time, just looking to get one more point right the next time. You get all 9, great, fantastic, but again, that's not really the goal. The goal is to improve with each FRQ that you do. Okay? Okay, email me if you have any questions. Take pictures if you tried doing the problem a different way and want to verify that you were doing it correctly. I'm more than happy to check that for you, but that's your first FRQ day.